Suppose that the positive axis of a one-dimensional coordinate system points east. How does the motion of a car traveling west change if its acceleration is positive? So if the velocity, right, the motion of the car, it's traveling west. So the car is going west. The acceleration is positive, which means the acceleration must be to the east. So if you have your acceleration one way and your velocity the other, this means that when V and A are opposite, that means in decreasing speed. Motion diagram, decreasing speed up an incline. This is direction of motion. Acceleration is opposite the direction of motion when you're decreasing. An airplane travels north, so here's the direction of motion. It doesn't change speed or direction, so acceleration must be 0. A ball is dropped and allowed to fall unhindered, so it's moving down. That's velocity. Oops, not pulse. It's velocity. And we know that when something falls, if it starts at rest, acceleration is in the same direction. It's increasing speed. This is constant. All right, we're back to this picture, but in this picture, similar to the previous one, we've got positive direction, right, always in the same direction as the motion. So the velocity on all of these is going to be positive, right? They're moving, because it says so, right? It says moving from left to right. So we're moving in this way. You'll notice, so this is positive, right? These are all going to be moving in the positive direction. Now, this one's increasing speed, you can see. This one's constant. This one's decreasing speed, so acceleration is negative. This one is increasing speed, so acceleration is positive. This is constant. And this one is going to be increasing speed in the positive direction. So I'm just trying to get a sense of what's going on. Now, I'm not going to go through and measure because if you remember from the first guided practice that these distances were the same, right, for A, D, and E. So we know that these now have the same sign so that those must be equal, and it's moving pretty quickly because it's covering a lot of distance. This one, and this one are all barely moving. It's much slower. So B, C, and E are equal as well. So this, because the axes are all pointing in the same direction as motion, all those speeds are positive as compared to when we did it last time, right? Because the axes were sometimes opposite direction of motion, we had some values that were then ranked as negative, which on the number line would be less, right? So that's the answer to this one. Since all axes are in the same direction as the velocity, no negative values to deal with. Okay, if V equals delta D over delta T is used only for average or constant speed, so this is a rule, right? This is true, and it's something that you should know. I recommend putting it on your Quizlet or your flashcards. Why can you use it to calculate delta D for a single interval, even if the object is clearly accelerating? So here's the thing. If you have, let's say you have whatever, this segment, and pretend this is like a road, like Grand Avenue, like a big, long, relatively long. You could find the average speed from beginning to end, right? Or you can find the average speed from B to C. Or you could find the average speed from D to C to D. Like the average speed equation is the average of all the instantaneous speeds. So when it's a big distance, that average speed is going to be, right, a big distance and a big time. So probably in reality, you're only really going at that speed only occasionally. Sometimes you're faster, sometimes you're slower. As you narrow that distance, this distance gets really small, but so does the time. So the average speed is actually more likely to be the actual speed during that interval. And that's how you can do that up to like millimeters. That's what our photo gate timers do, right? They actually measure the interval of time and they know the distance between, I think, is like 1.5 centimeters. It's a small distance and then you get a small time. So you can find the speed at that point. Okay, so we've got another ticker tape here, and if we want to draw a motion diagram, you can connect, you can kind of shadow these and you can see what's going on. You can see your increasing speed, kind of inconsistently, but it looks like you are. The signs, if you're moving to the right, like it says in here, this is going to be positive, positive, and positive. Use a ruler to find the first and last interval. I don't want inches. Let's see. The distance between the centers of these two, this distance is 1.4 centimeters. And this one is, I always try to do it from the center. This is 2.4 centimeters. So this one is dot every 1/10 of a second. So we've got our velocity, our initial velocity, delta d over delta t, 0.014 meters. I'm going to convert it first, unlike what I did last time. This will be 0.14 meters per second. And then for this one, it's going to be 0.024 centimeters in 0.1 seconds. So it'll be 0.24, oops, this is meters per second. So that's how you do those calculations. These are going to be where we draw the labeled sketch. This is a really important skill. Please don't skip doing these. You're going to be required to do these in order to move to the proficient level on any problems that you come across. So you've got the skier, and I'm going to do V, X, and T. You might ask, well, how can this be X? Well, we're actually going to tip our axis. We're going to make positive be along the incline. Some people like to call this the line of action, or you can just call it the positive X. That's fine. And the Y is going to be perpendicular to that. And then they get, she gets down here. And this is going to be VXT. We'll call this 2. This is 1. And between these two positions, there's an acceleration. So she begins from rest at the top of the mountain. For the first part, she speeds up at a rate of 7 meters per second squared. She reaches a top speed of 27. And what is her displacement? So we know these are both 0. And this is what we're looking for. So this one. And let's draw a quick motion diagram. So we know we're increasing speed, and so velocity, acceleration both point down. That means that our acceleration is in the same direction as our positive axis. Okay, a man is driving at a constant speed. So here's the car. He's just kind of buzzing along. And he sees a deer, the distance 300 meters ahead. Oh God, I don't know how to draw a deer. Here's a deer, little ears and antlers. How's that? Did I do okay? All right, there's my deer. And so the initial velocity of the car is 20. This X is, we're going to call this 0. Oops, this is time, is 0. Okay, and then this is where the deer is. This distance, I'll call this X of the deer, is 300 meters. His reaction time is 0.15. Now, reaction time, what this means, like, look, after which he applies the brakes. So that means that he's going at constant speed during this time interval where he goes, oh, there's a deer. I got to move my foot. And then moves his foot towards the brakes. So we don't know what distance that is. And then it says after which he applies the brakes and decelerates. So we want to know how far does he travel between the time of the initial sighting and putting his foot on the brakes. We actually want to know, does the car stop? We hope so. We don't know. We don't know this. We don't know this. We hope it's less than 300. We know we want to come to a stop. We know that the braking is 7.5 meters per second squared. Oops, sorry. Meters per second squared. So this is actually a 3-step problem that, yeah, 2 stages, 3 steps. And this part here, the motion diagram is acceleration equals 0, where this one, you're still moving to the right, but you're trying to slow down. So you can see if you make to the right positive, then this acceleration is going to be a negative number. So how did I know to break this up? Well, part of it is experience, right? Some of these cues, when I see reaction time, right, and this word after which he applies the brakes. So we have these 2 stages. While you're reacting, you're moving at constant speed. And then once you do react, you're going to slow down to a stop.